This is the second of 3 videos we developed to describe our research program aimed at improving evaluation by combining computer modeling with traditional evaluation methodologies. We want to see if decision makers get better insight about their programs if evaluators go back and forth between traditional evaluation and computer modeling. In particular, we want to see if this back and forthing works best when it continues over the entire life cycle of an evaluation. We have special reasons for using a particular kind of modeling called agent-based modeling, but more on this later. In this video, we will cover topics that explain the history of our work, its intellectual foundations, and where we are now. In the next video, we'll show agent-based computer modeling of an evaluation of the Arizona General Education curriculum. We will show you how the model runs, what it tells us that traditional methods can't, and the value of combining traditional analysis with modeling. By we, I mean Johnny Morell,
Van Paranak,
Melanie Wallach,
and
Kirk Nestus.
For all of this, we thank the Faster Forward Fund. The essence of evaluating a program is to address 2 questions. How does my program work, and what has it done? To answer these questions, the first step is usually to develop a pictorial representation of the program and of its consequences. Essentially, we develop a model of the program. When we develop these models, we would do well to remember George Box's famous aphorism, "All models are wrong, but some are useful." Why is this true? It's true because models are useful when they show relationships, and relationships won't be visible amid too much clutter. So much for models in general. What about models in evaluation? Why are they useful? The obvious answer is that they help us understand relationships between program parts and outcomes. But models are useful in evaluation for other reasons as well. They help people see what the outcomes of their programs may be. They help people see implicit assumptions about how their program works and what it can do. They facilitate the use of evaluation findings by priming people for what data to expect and why the data are useful. They help develop agreement about the what that is being evaluated. Because models are so important in evaluation, we evaluators have spewed forth numerous books, articles, training materials, and collaboration websites that are loaded with craft knowledge about how to construct them and what they should look like. Of course, we have many different opinions about the visuals and content of a good model, but really, all the differences amount to differences about style, form, and the characteristics of a good graphic. In the end, all our ways of depicting program behavior and outcome are pretty much the same. Most important, all our models are static. They are pictures with no moving parts. It's impossible to change one part and see how the others move. We think that static models are limiting. Why are static models problematic? Here's an example of a model for a program that is trying to support the adoption of a new proven best practice in an organizational setting. It comes from some early research that we did. By using it here, it does double duty by giving you some information on the origins of our research program. At the core of the model, we have a feedback process. If people have confidence in the practice, they will use it. If they use it and they like the result, they will use it more. If they don't like the result, they will use it less. This gives us an outcome, a behavioral factor, and a psychological factor. We then add 2 other components. One is organizational, training, and one is psychological, skill. The program theory is that if the training is any good, it will influence both confidence and skill. Next comes organizational support that directly influences use. Or put another way, if your boss tells you to do it, you'll do it. Finally, we add a social factor. Do your colleagues use the new practice? If they do, that use will increase your confidence. It took us less than an hour to conjure this model for some early research that we did. The process involved lots of napkins and coffee. It took longer to make the picture look pretty than it did to outline the logic. We were really surprised at how many people liked it for so many different applications. We have no idea if it depicts reality, but it certainly seems plausible. So what's the problem? The problem is that it looks so plausible that people seem to be willing to use it. The fact that the graphics are pretty good doesn't help. That just makes the model even more appealing. Wouldn't it be nice to test the model before we went to the considerable effort of building methodologies and metrics for it? Wouldn't it be nice to have a bit more confidence in the model and on the program it described before the program and the evaluation actually started? Wouldn't it be nice to keep testing the model as evaluation data came in and to use the model to adjust the evaluation? We used the model we just showed you to build an artificial scenario to test our notions about the value of combining modeling and traditional evaluation. The exercise was instructive. It provided all kinds of insight that we would never have had if we only worked with the static model. We questioned assumptions about how the program should be designed and about what the program might accomplish. We gained knowledge about what evaluation data would be needed and how the evaluation should be designed. With this experience under our belts, we went looking for some real evaluation data to use, and we found it in the Arizona General Education curriculum.
The Arizona General Education Curriculum, or AJAC, is a higher education policy and process roadmap created to guide Arizona post-secondary students toward completion of general education requirements, the goal being to ease transfer from the state's community colleges to four-year universities. The AJAC details these so-called Gen Eds as 35 to 37 credits, so 11 courses, in areas like writing, math, arts, and humanities. Arizona has three types of AJAC, each with a form that students can use for planning. Because AJAC was developed collaboratively by institutions across the state, all parties agree that satisfying the requirements of an AJAC assures community college students can transfer to any Arizona university and that their credits will apply toward completion of a bachelor's degree.
At the time we entered the picture, the AJAC evaluation had already been completed. As a result, we couldn't test our original vision, which involved combining modeling and traditional evaluation over the entire life cycle of the evaluation as the data were being collected. Rather, we had to test a variant of our vision. While we could not revise the evaluation over time, we could use the model to guide reanalysis of the existing data, and that is what we did. We are about to show you the model, but before we do, we need to spend a little bit of time explaining what we mean by the term agent-based modeling, a phrase that we have been tossing about way too casually. We have presentations and articles if you're interested in knowing more, but here is a quick once-over. There are two ways of doing modeling. One way looks as if it is automating connections among parts of a model that describe a system. The easiest way to think about this is to imagine a typical logic model. Those models have boxes to describe the elements of the program and the outcomes, and arrows to indicate inputs, outputs, and feedback loops. A systems dynamics model would add details on how fast things were moving into and out of the various elements, and how much of what could be stored in each element. It would then stuff the model into a computer and let it run. This is a good thing to do, and we think that evaluators should do a lot more of it, but we prefer a different method of modeling. We like to use a method of modeling called agent-based. It's a different tool for doing modeling, but what's really important is that it's based on a different way of understanding how the world works. It's not a better way, but it is different, and it does provide insight that other methods don't. And sometimes that different kind of knowledge is helpful for understanding why programs work as they do and what outcomes they have. To understand the difference, Let's start with about a minute and a quarter recap of some principles of research design and statistical inference. After the recap, we'll give you an example that will last about 2 minutes and 15 seconds. We think the material is important because we think that evaluators should know more about topics such as complex behavior, sensitive dependence on initial conditions, and emergence. But the truth is that you won't lose much of our story if you fast forward over the explanation or over the examples or both. When we do research, we care about units of analysis, which can be people, classrooms, county governments, street intersections, wetlands, automobile engines, mental health programs, or anything else that we want to know about. What we learned in school is that we should care about how groups of units of analysis behave. We are taught not to care about individual units. We are only supposed to pay attention to average scores and to how those scores are spread out. That's fundamental to classical research design. It's an approach that can teach us a lot about how programs behave. It's yet another method that we think evaluators should respect, admire, and use. But as with all tools and methods, it's not universally applicable. There are things it can miss. Mostly, we miss knowing about how systems can end up differently because of small local changes in how units of analysis interact with each other. Or to use some of the current buzzwords, we miss observing emergent behavior in complex systems that results from sensitive dependence on initial conditions. Another way to think about this is to think about what happens to individual scores as an analysis proceeds. In our traditional way of doing things, the very first step is to obviate individual scores by combining them into summary statistics such as means, medians, and variances. In an agent-based perspective, the individual scores are carried throughout the entire analysis, not to ignore group behavior, but to explain it. That explanation was pretty abstract and opaque, but maybe an example will help. Let's say that we are evaluating a new way to teach kids math, and that our unit of analysis is the classroom. In other words, we are focusing on the average math score of all the kids in each class. Now, think of how two classrooms might differ entirely by chance. In one class, there's a group of kids who are popular and who are also excellent at math. In another classroom, the popular kids hate math. It's not hard to imagine that as teachers began to teach math, the trajectory of achievement in one classroom would be very different from the trajectory in the other class, with one class ending up with a high achievement score and the other with a low achievement score. In terms of teaching math, the new curriculum would be equally good in both classes, and on average, across the entire school district, math scores would improve. But a classical research design would not be able to capture the different learning trajectories in each class, while an agent-based approach could. Remember that I have been using the phrase trajectory a lot. That was not an accident. What I mean is that as teachers began their semester, by chance, one classroom had a set of initial conditions, a group of popular kids who were good at math, while the other class had a different set of initial conditions, a group of popular kids who hated math. As kids began to learn math and interact with their classmates, the learning paths in each class diverged. Why might an agent-based approach reveal this kind of behavior and classroom outcome? Because in the model, students would be agents, and their interaction with overall classroom achievement would be captured. In the next section, I'll get a bit more technical about what agents and their modeling is all about. It's another topic you can fast forward through if you're so inclined. In the previous slide, we gave some examples of what agents can be. But the question remains, what does an agent have to be able to do to qualify as an agent? The answer will take about 2.5 minutes. We think it's worth listening to, but skip ahead if you disagree. Two qualifications will get something into the agent club. The applicant must be able to sense its environment and react according to a set of rules. But how do we move from having agents to having an agent-based model? We are going to answer this question by using the AJAC model. We'll only refer to it briefly in this video. We'll get into its guts in part 2. We begin by developing a model of the system that we want to evaluate. For instance, take the AJAC model. With the model in hand, the first step is to identify the agents that populate the model. In our case, it's students. The next step is to specify 4 kinds of factors. What decisions do agents get to make, e.g. enroll for the next semester or not? Agent performance, e.g. how many credits did a student accumulate? Model relationships, e.g. how much weight does a student give to the opinion of his or her peers? And environmental variables, e.g. how many credit hours are needed to graduate? Once these decisions are made, what happens? What happens is that the agents are dropped into a cyber world and told to take stock of themselves and of their surrounds. For instance, in the AJAC model, students are asked to consider how close they are to graduating, how fatigued they are, and what support they're getting from family and friends. Based on those considerations, the student makes a decision about enrolling, and by so doing, experiences a new set of conditions and influences. For instance, the new semester will bring about a new achievement record, a new degree of closeness to graduation, and so on. In other words, the student's world changes as he or she faces a decision about the next semester. It's important to keep in mind that we are not offering this example as the be-all and the end-all of what an agent-based model can be. We only want to provide a sense of how one can move from having agents to having an executable agent-based model. That's the process, but keep in mind that agent-based models can have many interesting complications. For instance, models can have rules that change in systematic or random ways as the model runs, multiple kinds of agents, some of which are nested within each other and some of which are not, and shifting environments. We've been talking a lot about moving from a static model to an executable one. To do that, we used an agent-based application called NetLogo. Even if you never plan to program an agent, it's worth downloading this software and perusing the model's library. There's no end of interesting stuff in there. Here is what the transition from the static to the executable model looks like. There's a lot going on here. We won't go into the gory details in this video, but we're happy to talk about them ad nauseum if you are interested enough to call us and ask. But here is the brief once over. These sliders tune the input to student motivation. They include fatigue, social influence, class performance, and closeness to graduation. These drop-down menus let us sample students along 2 dimensions as they transfer from community college to a 4-year university. AJAC only, non-AJAC only, and both. Associate's degree only, non-associate's degree only, and both. This graph shows the number of graduates, dropouts, and current campus population as students transfer into college, graduate, or drop out. This graph is a histogram of motivation levels among the students. This is a plot of each student's motivation against closeness to graduation as he or she moves through school. This is the kind of knowledge that agent-based modeling excels at. Here is a peek at the code that makes it all run. These are the sliders that adjust the relationships in the model. For instance, it's one thing to say that closeness to graduation affects motivation. It's another thing to choose a mathematical function to show how the relationship changes. In this model, we are able to change the settings for each of the specified parameters. And herein lies a cautionary tale about moving from static to dynamic models. Each of these sliders adjusts a mathematical function that is contained within all that programming. In other words, programming the model requires making a host of assumptions that are easily buried behind the magic curtain of lines of code. That's okay, but it is something to be acutely aware of when building and interpreting models.